lost 9.
No, honestly, I haven't been keeping track.
Right here.
Okay, because it depends on if you start at 0.
Oh, yeah, it's 9.
0 was a linear algebra, I think. So, yeah.
Let's just say 9.
Oh wait, I called it 1.
Yeah. You finished the final project? Wow.
Don't say that. I don't think it's complex enough, but
Great, cool. Okay, cool. So today we're going to be talking about everything to do with dynamics, which I think you guys have probably finished up at this point. Did you guys start controls yesterday? Or okay, great. Sounds good. Yeah, so today we're going to talk about a couple of different things that are pretty important to dynamics. So we're going to start by talking about what energy is, how we can describe it for some simple systems, just for particles. We're going to talk about why we need dynamics as well, like what it actually gives us and what the point of doing this whole process is for robotics. After that, we're going to start out by motivating Lagrange's equations, and we're going to show that they're actually just the same thing as F equals ma, just a fancy version. We're going to do that same thing again for rigid body dynamics, and then all the way at the end, we're going to tie it together with a couple of examples. All right, so before we get started, do you guys have any administrative or like general questions?
so on the second major, right?
Yeah.
Dynamics, like what's the breadth of that?
There's going to be one dynamics problem, and then so it'll be like one vision. The vision one will be pretty short, probably. Yeah. So there will be like a rigid body / Jacobian one, vision one, dynamics one, and small control sets. Yeah. 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 What's up? Oh shoot, there will be a Ross question as well. yeah, but it'll be shorter than last midterm. You guys all have time.
Okay, yeah.
So don't worry. Yeah. Yes, the problems will be on the shorter side compared to the last one. Yes. Yeah. But there's no final, so that's all good. This is going to be your last time.
The next Thursday is like classes over.
Yeah, there's just going to be guest lectures after that. So we'll have our last section next Wednesday. And then I know, oh my God, what am I going to do for the rest of the semester? Yeah, we should talk to the readers. I don't know what to do. Yeah, maybe. What's up? All right, cool. So did we have, just any questions before we get started? Or you guys think? Get into it. All right, very cool. Okay, so let's start out by talking about what energy is, what the different types of energy are, how they arise in our systems in dynamics. Okay, so in this class, we're really going to be talking about two main types of energy. Okay, so two main types of energy. All right, so the first of them is kinetic. And then the second one is potential. Okay. All right. So if you haven't taken physics before, don't worry. If anything sounds unfamiliar and you feel like we just breezed over it, just let me know, and then we can come back and talk about that in greater detail. Okay. All right. So let's start out by talking about what kinetic energy is. Kinetic energy. We're just going to start with like a conceptual overview of like what it is and how it shows up in systems, and then we'll get to a little bit more of a mathematical level. Okay. So our general idea with kinetic energy is that whenever a body is moving, say like my water bottle, for example, right? Moving it across the screen, going back and forth, it takes some amount of effort for me to stop this water bottle, right? If it's moving and then all of a sudden, boom, I just stop it, right? My hand has absorbed a lot of force from that. It took some effort for me to go ahead and stop the motion of that water bottle in its tracks. Okay. So what kinetic energy really is we could think of it intuitively as how hard it is. How hard it is to stop a moving body. Okay. So this is going to depend on a couple of different things. All right, let's just sketch out a couple of simple scenarios and see if we can gain some sort of intuition for what a formula might be for this. Okay. So if I have a mass and it's moving with a velocity in this direction, right? Small mass over here. Then I have some big mass, capital M, it's moving with the same velocity over there. The larger the mass is, the harder it is to stop it when it's moving through space. Okay? So larger mass equals harder to stop. And that, in turn, will mean that we have a higher kinetic energy, right? Higher kinetic energy. Now, the same thing for the actual velocity, right? If we bump up the velocity of that object, so we're sending it super quick across the table, right? That's also going to make it harder to stop, okay? So larger velocity equals higher KE. All right. Now, what else do we know about this kinetic energy? Does the direction of our velocity actually matter? Well, say that I have my mass, right? And I'm moving it in this direction over here with a certain velocity, certain mass. And then I do the same thing, but in the other direction, okay? Mass, same velocity, just pointing in an opposite direction. In this case, it's going to be just as hard to stop it in one direction as it is in the other. Okay? So just as hard to stop. Hard to stop in one direction as it is in the other. Okay, so this tells us that kinetic energy doesn't actually depend on the direction of our velocity, right? It just depends on the magnitude. Okay, so general idea, kinetic energy just depends on the magnitude of velocity. All right. Okay, so putting these ideas together, we can come up with sort of simple formula for what kinetic energy is. All right. So in dynamics, we refer to it with this variable t. I'm not too sure why it's t. I asked someone once and they just said, that's just convention. And that was my answer. So in general, we say t is our kinetic energy. And that is equal to 1/2 times the mass of our particle. Okay. So mass of particle multiplied by its velocity, dot product with its velocity. Okay. So in general, this is what we're going to use to describe the kinetic energy. All right. So let's see how this sort of matches up with those properties we were talking about up there. All right. Well, we know that when we increase our mass, right, we're going to have a higher kinetic energy. It's harder to stop. When we increase our velocity, we're going to have a higher kinetic energy. It's harder to stop, right? That's what we see from our mass and our velocity being directly proportional to this kinetic energy, right? And finally, we discussed that other property where we said that the direction of this velocity doesn't actually matter, right? So if we take a close look at this v dotted with v, we know for any vector, v dot v is going to be the square of the magnitude of v, right? So this kinetic energy is only going to depend on the magnitude of our velocity, okay? It's not actually depending on the direction, all right? So what this is it is a scalar that tells us energy associated with movement, okay? Movement. All right. So that's our general idea of what kinetic energy is going to look like for a single particle, all right? So we're going to talk about the rigid body case a little bit later. It's going to be somewhat more complicated, but it's going to have the same central idea of mass and then magnitude of velocity squared, okay? So do we have any questions about like the basic setup for kinetic energy? How do we feel? All right, cool. So let's then move on to talking about the other type of energy, right? Potential energy. So potential energy. Okay. So this kinetic energy was telling us about how much energy we had from moving every split second. All right. But what does a potential energy do? So potential energy, or PE, I'll abbreviate it, tells us about our ability to gain a high kinetic energy. High kinetic energy. Okay. So if we place our particle or a mass or whatever in a position where it's going to be able to gain a lot of speed, right? Then it's going to have a very high potential energy. Okay. The simplest example of this is that, let's imagine that we put a particle on the edge of a cliff right over here, right? So this is pretty tall. It's got this height, capital H over here. And then we also put that same particle on this other little cliff, right? Small h, right? The mass is going to be the same in this case. Now, in this case, we have a high height h, which means that as it falls, right, it's going to be collecting a huge amount of velocity, right? It's got all this room to gain a lot of kinetic energy. So because we have the potential to gain lots of kinetic energy, we say that we have a high potential energy, okay? We have a high potential energy, all right? Now this one on the other side, h is pretty small, right? At least compared to the other one, okay? So we have less kinetic energy that we can gain. Okay. So earlier, we had talked about these different elements that go into generating a kinetic energy, right? We said it's mass, this velocity, we don't care about direction. Now let's try and do a similar thing for this potential energy, and we'll see if we could break it down into the terms that we need to, get an actual equation for it. So one thing that we've seen is that, let's see, what is important to potential energy? Okay, so the first thing that we just saw up there is that what's important is a height relative to a certain surface, right? A height relative to a surface, right? So it's not actually like a physical height with respect to like the center of the earth that actually matters for us. Yeah.
What is on the, because we have to measure that because
Where
We have.
oh yeah, like a flash sheet that I use for this. Yeah. All right. So what we really care about is a height relative to some sort of surface out there, right? We could just take a reference, say, like as the table, and then I drop a ball, and then like, wow, relative to that table, I have that ball high up or low down. Okay. So we don't need an absolute height with respect to some physical point in space, right? That's never going to exist, right? If you pick the Earth, there's always the sun. If you pick the sun, there's always the galaxy, so on and so forth. Okay. So we just want to pick one height relative to something else. Okay. Now, what else matters for us? Well, the mass of our ball, of our particle, might matter, right? Because we know that mass is something that's really important to our kinetic energy. And if we're interested in something that tells us how much kinetic energy we're able to gain, then we should definitely be including that mass in there, right? So we want our height, h at the moment. We want our mass, m. And then what else do we want? Well, this one in particular here, this is all about gravitational potential energy, okay? So there's a couple different types of potential energy, but the most common one we'll encounter in this class is just that due to gravity, all right? So something that is important to this idea of how objects fall is this gravitational constant g, okay? So gravitational constant g, okay? And this is something that tells us that if we drop any particle out there, it's going to fall with the same acceleration g, okay? So drop any particle will accelerate with g. Accelerate with g, okay? So usually you'll see g like equal to 9.81, and the units of acceleration are meters per second squared, all right? So this is a common value. This value doesn't matter too much in particular here. I don't think we'll ask you to solve too many numerical problems. But yeah, just keep that in the back here. Okay. So this gravitational constant is telling us how quickly we're going to be picking up speed once we drop our object, right? So it tells us how quickly we pick up speed. How quickly we pick up speed. And because of that, it's also really important to this potential energy, okay? So we want our gravitational acceleration, or g, all right? So all of these are going to be things that are positively increasing our potential energy, okay? So all up, what we say is that our potential energy due to gravity, which we call V due to gravity, is equal to our mass times gravitational constant times the height with respect to some surface out there. Okay, that's just our mass, gravitational acceleration, and our height. Okay, and that's what gives us our gravitational potential energy for a single particle. All right, so do we have any questions about this one over here? Okay, cool. So something that we see is that this one is also a scalar, right? So what's really important to keep in mind about these energy quantities is that they're not vectors, right? They don't have directions. They're just going to be these simple scalars that are telling us, you know, at this point, how much of a certain quantity or how much of a certain ability does our system possess? Okay. All right. So let's just talk about one other type of potential energy before we continue. So spring potential energy. Potential energy. Okay. So we had this idea before that when we move to a different position, right, in space, when we moved our particle up, right, all of a sudden we gain this potential energy from an ability to, you know, gain a lot of kinetic energy back on the way down. Now, it turns out that this sort of concept where we gain energy by moving to a different position, something that applies to a lot of different scenarios out there. Okay, so one of those is with a spring. So we'll denote a spring with like this little squiggly line right here. Looks like a resistor. And let's put a little mass on the end. Okay, let's say that our distance from this over to here is going to be x. All right. All right. So as I stretch the spring, what's going to happen, right? Let's say that I stretch the spring all the way over here, such that my mass is now in this position. When I let that spring go, right, this mass is just going to go flying back in the other direction. It's going to gain a huge amount of kinetic energy. Okay. So when I let go of the mass, let go, we gain lots of kinetic energy. Okay. So just like we had a kinetic energy that we got from dropping something from a high height, right? By putting energy into it, by bringing it up and dropping it, gaining a bunch of kinetic energy. We're doing the same thing with this spring, right? We're taking this mass, we're pulling it out, we're releasing it. Suddenly it's picking up all this heat, okay? So we have some sort of kinetic energy, or excuse me, some sort of potential energy from the spring as well. So we also have a spring potential energy. Awesome. So what would that look like? Let's check out some of its properties, right? So our first one is that, say we have our mass in this direction over here, okay? And we've stretched it out a little bit, right? Maybe it wasn't originally in this position. Maybe it was a little bit closer to the left. Let's say now that I'm going to go and I'm going to stretch it to the exact same position on the other side, all right? Mass over here. Now, does my spring actually care whether it's been pulled one side or the other, right? Like if I pull my spring all the way in this direction versus if I pull it all the way in that direction, it's actually going to give me the same amount of energy back, right? So if we pull it in either direction, we get the same kinetic energy back out when we release it, right? Why was this? Well, this was just because our actual kinetic energy didn't depend on the direction of our velocity, right? So we have like a velocity v pointing in that direction, then we let it go. And we have a velocity v pointing in that direction, then we let it go. As long as the magnitudes of those are the same, we actually don't care about its direction, right? So we have this property that our spring potential energy doesn't depend on the direction in which we stretch the spring. It just depends on how much we stretch it, okay? It just depends on how much we stretch the spring. Okay, cool. So we can, based off of this idea, essentially just come up with another formula for energy. And this time it's going to be V spring. Once again, V is just representing that potential energy of the system equal to 1/2 K times X squared, okay? So that squared is essentially indicating that if we have a positive or a minus displacement, positive or minus stretching of the spring, it's going to come out to be the same, right? So plus or minus doesn't matter, right? That squared is just going to take care of it for us. It's going to make everything positive, okay? Now this K is called the spring constant. So spring constant And this is essentially just something that tells us how hard it is to actually pull our spring apart, okay? If I have a spring that's super, super hard to stretch, that means that I'm putting a lot of energy in it when I'm trying to get my particle out somewhere, okay? So if I let it go, it's gonna pull back in with a huge amount of energy, okay? So that's how hard it is to stretch the spring. All right. Okay, cool. So yeah, that's our spring potential energy right there. Do we have any questions about how we got to this point with our potential energy? You know, at the moment, this might just be a review of some physics stuff. So it's early days, yes, but we'll get into some exciting stuff pretty shortly. All right. So a general summary is our kinetic energy is denoted by this letter T, right? Kinetic energy. So that's energy of motion. And our potential energy is denoted by this letter V, okay? And that tells us how quickly we have the ability to go, okay? So you could think of it like an energy that's stored in our system, stored energy. All right, great. Yeah, it's like if we release it from a high height, it can go super fast. We'll have a high potential energy. Okay, cool. So do we have any questions just about this general idea of energy before we go on and sort of motivate this problem of dynamics and this whole field? What do you guys think? Good. All right, cool. Okay, so we're going to start getting a little bit more mathematical now, getting more into the content we've been discussing in this class. All right. So our main question here is, what is dynamics? Right? Why are we covering this sort of thing at all in the class? Yeah. Yeah, sure.
So potential energy always be positive. Sometimes for the origin.
Yeah, like above our reference. Yeah, so your potential energy won't necessarily be positive. And that's not something that we really care too much about, because usually when we're doing like dynamics for a system, what we care about is our change in potential energy. So if we have a decrease in potential energy, that means that we've been fallen. So if we start in a negative position and go to an even more negative position, that change is still positive. So it's really just going to be the change in potential energy that we care. Yeah, that's a great point. Okay, so we care about change. And that comes from this idea that all that we're doing for this potential energy is just setting some sort of reference position for it. So if we take the difference between those, then the reference position will just subtract out, right? All right, yeah, great point. Okay. Normal. Okay, great. So let's talk about this question of what dynamics actually is, right? So our basic idea for dynamics, is we want to be able to find the equations of motion for any system out there, okay? So we want to find equations of motion for any system, no matter how complex, right? So if we just look at something super simple that we've been talking about, right? Like a ball falling down, okay? It's moving down under the force of gravity. It's tracing out this path as it falls, right? Gravity's pointing down. And maybe it's like moving along in the z direction, some coordinate system, right? If that's our z, that's our y, that's our x, right? Its z coordinate is changing as it goes along in time. So our question in this scenario would be, what is the function z of t, right? How can we solve for the actual function that describes where this ball is going as we drop it, right? Where this ball is moving as time passes on, okay? So this is actually something that's really, really powerful that will extend way like far beyond these simple examples that we're doing right here, right? So one more robotics oriented example is a drone, right? This is something that you guys will talk about on your next homework, okay? So let's imagine that you have some sort of quadrotor drone, and these are your little propellers, little circles on the end over here, okay? And let's say that we want our drone to track some position, x of t in space, okay? So what effect will a thrust force have on the joint position, right? This is going to end up being super complicated, right? We have these rotating propellers that are applying a moment to our system. We have these forces that are also applying moments. They're moving it up and down in space. All of this super complicated dynamics is going on here, okay? But what this boils down to is we want to actually figure out an x of t, right? This time it might be in 3D space, right? We want to figure out the x coordinate as a function of time, the y coordinate as a function of time, the z coordinate as a function of time. But our main thing is we just want to know where these things are going when we give them certain inputs, okay? So another example would be with our robot arms, right? So if we're trying to design, say, like a feedback controller for our robot arms, well, something that might be important to know, right, is if this is our simple robot arm, right, like that's a joint over there, and like that's another joint over there, and that's our hand, and we have this position x of t on our hand that we'd like to control, right? We might ask the question, how do the torques that we apply on these joints, right? How do these rotational forces impact the position of our robot arm in space, right? So how do joint torques impact position? Right? Now we have all these different factors to think about, like friction on each of the joints. We have a mass on each of the joints. These are all rigid bodies as well. There's a lot of super complicated math that's going on to describe these equations of motion, okay? So this idea of dynamics is that we're really just devoted to this idea of figuring out how we can find these x of t functions, right? X of t, y of t, z of t, maybe a theta of t for a system that's rotating, okay? So it's the study of applying physical laws to figure out those equations of motion so we can know how our systems are going to act in a very reliable way. Okay? Oh, yeah, sure. Yeah.
And then, oh, z of t, like the position in the y direction?
Yeah, it's like this position. Or z of t. Sure, yeah. All right. So how do we actually go about finding these equations of motion, right? So how do we find these equations? Right? Like, what does that search even look like? You know, like so far we've been doing all of this stuff with forward kinematics, inverse kinematics. Those are just simple like geometric relationships, right? We never involved forces in there at all, right? So now we're looking at what happens, say, if I push it with a certain force, how's that system going to respond, right? We're not just looking at what happens when we plug in a certain joint velocity. We're trying to do somewhat of the inverse problem, right? We're saying when we apply this force to the system, where's our joint velocity going to go? Then how will our entire system respond to that, okay? So now we're asking this much more complicated and detailed question, okay? So how do we find these equations of motion? Well, something that you guys have probably seen before, right, is this equation F equals ma, right? So this is the sum of all forces, right? Those could be vectors over there, right? We could have a force in the x direction, the y direction, the z direction. This is going to be the mass of our system, and that's going to be the acceleration of our system, okay? It turns out that using just this equation, we can actually figure out the dynamics of a lot of systems out there, okay? And this comes from this idea that this equation, F equals ma, it's not just a simple scalar equation, it's actually a differential equation in time, okay? So this is actually a differential equation, okay? So why is that? Well, acceleration is the time derivative of velocity, right? ddt of velocity, which in turn is the time derivative of position, right? So ddt of dx dt, right? So acceleration is actually equal to the second derivative of position, right? Like d squared x dt squared. We can write it, okay? So if we write out this thing in full, F is actually not just equal to ma, right? But more in a more, like, I don't know, advanced way, we could say. We could write it as m d squared x dt squared, okay? So now what this equation of motion is it's really a differential equation in terms of x that we need to solve to find our x of t, okay? So how do we solve? F equals m d squared x dt squared for x of t, okay? So this is our main question in dynamics. So how do we find this equation of motion, right? How do we find what all of our forces are? How do we find an expression for this acceleration? and how do we solve that equation? Okay, so we have a two-step problem. So one is find or set up equation, and two is solve or study equation. Okay, so it turns out that for our really complicated systems, these equations are actually going to be unsolvable by hand 99% of the time. Okay, so if you look at a quadrature example, you can actually prove that there's no elementary solution for that. Even something as simple as a pendulum, there's actually no elementary function that you could use to describe this equation of motion. So it's super, super complicated, right? These equations can get really, really crazy. We have like squared terms in there. They have no guarantees to be linear. All this nasty stuff is going to pop up. But we'll see that there's actually a lot of nice conclusions that we could come to about our equations of motion without actually solving these equations directly. Okay, so we'll talk about some of that stuff a little bit later. But for now, just keep this sitting in the back of your mind, right? F equals ma. It's actually just a differential equation that we want to be solving for x of t. Okay. So before we continue, there's actually one more point that I want to make about this equation. All right. So this was not actually the original form. The original form that Newton wrote. Newton actually expressed this equation when he came up with it in a little bit of a different form. Okay. So instead of writing F equals ma, he wrote it as the following: F equals dg dt. Okay. So G, something called the linear momentum. Linear momentum of your particle. Okay. So the only thing that that's equal to, it's pretty simple. It's just the mass of your particle multiplied by the velocity of your particle. All right. So it is a vector, right? Since velocities are a vector. And we're just saying that the time rate of change of our momentum of our particle must equal all of the forces that we're putting into our particle. Okay. So another way of looking at F equals ma is saying that sum of all forces equals rate of change of momentum. All right. So we're going to come back to this idea in a little bit when we talk about what some of those partial derivatives in Lagrange's equations actually mean. Okay. So this thing's going to come around. We're going to see it in maybe a couple minutes. All right. So do we have any questions about this setup with F equals ma? Like why we're trying to solve these problems or what these equations are sort of giving us? How do you guys feel? Oh, rate of change. Yeah. So, oh, so I'm just saying right over there that this is a vector. So a vector in R3. Yeah, sure. Right. So ROC equals, yeah, rate to change. Okay, so just remember whenever you see this G, it's a momentum, all right? So it's just the mass of your particle multiplied by its velocity vector, okay? So mass times velocity vector.
Instead, you put over here.
Oh. Sorry.
I wrote it down.
Okay, so do we have any questions about this stuff? Any other questions?
Yeah, I think it wasn't.
There's a G, right?
No, I think we wrote 8.
Oh, it. Okay.
It looked like.
No, yeah, that's what I was asking.
All right, yeah. All right, thank you. Yeah, H is actually angular momentum sometimes. So don't get that mixed up. That's also a vector, I guess. But...
Life is a vector.
G.
Wait, like yeah, like because it wasn't always like little p.
Yeah, so some of them they use P, like it depends on like what book you look at. Like some of them are G, some of them are P, and then kinetic energy like is usually K when you start out, and then suddenly they just switch to T for some reason. I don't know. Yeah, like a lot of the letters that they use in here and then in controls as well will come from German and Russian. So maybe I don't know, the word for like momentum in German starts with a G. That could be, I don't know, could be where it comes from. Sounds about right. Yeah.
It's like controller with a K, because in German it's called.
Yeah.
So that might actually be why.
Yeah, so the reason they use like the letter U for control inputs as well is that U is apparently like input in Russian or something. Yeah, because there's this guy like Pontryagin who's Russian that came up with a bunch of that stuff. Yeah.
Sorry.
Oh, yeah.
Oh, no, it's on the couch.
Oh, okay. Alrighty.
All the Europeans developed this.
Yeah. So. Yeah.
Who's that guy from?
Yeah.
French.
Okay, so let's talk about Lagrange's equations. Let's try and come up with some sort of interpretations for the form of Lagrange's equations, where they come from, and what all those different partial derivatives mean. What's actually going on? Okay. So why do we actually want to use Lagrange's equations, right? Why isn't F equals ma good enough? So what's wrong with F equals ma, right? Why don't we like that? Well, let's say, for example, that we're looking at this sort of system over here, right? Where we have an angle like θ1, and then we have another angle θ2, right? If we're trying to do like F equals ma for this system, we need to figure out somehow like what the acceleration vector is, like what x double dot is going to be for our system over here, okay? And the more links we add, the more complicated this starts getting, right? It's going to get super hard to find x double dot, right? Because this thing is a vector in space, right? It's not just a single scalar acceleration, it's a vector, right? So we're going to have to be adding all these different vectors, taking a bunch of different derivatives. They're all going to depend on sines and cosines everywhere. It's going to be a huge mess, right? So our first thing is hard to deal with this x double dot, right? Hard to find acceleration. Now it can also be hard to find forces. Okay, so in this scenario, right, we want to figure out what the force due to gravity will be on this, right? And write that in terms of like our θ1 and θ2, or maybe we have some like normal force over here, or like a frictional force over here. It's going to be kind of hard to resolve all of those different contact forces that are going on between these rigid bodies. Okay, so what Lagrange's equations do, so Lagrange sort of abstracts all of this away behind energy. Okay, so we abstract away behind energy. So remember, energy was just a simple scalar value, right? If we're trying to add up energies, we're just like adding 1 and 2, or like 10 and 15, something like that. Okay, so it's super easy to add and work with energies, take their derivatives, right? Those are just scalar quantities. So that's one thing that's nice. Okay, and then another thing that's nice is that we don't actually have to deal with contact forces. So we don't deal with contact forces. Okay, so if we were to take a Newtonian approach to try and solve this problem, right, what we would do is we would break it into two pieces. It would say, okay, there's going to be a force on this, there's going to be like a force like that, and then they're going to be the opposites in this direction. Okay, so we would have to solve for these force pairs, set up a system of equations, and solve for the contact forces between these two parts of the pendulum. All right, now what Lagrange is saying is that, okay, we're just going to look at the total energy of our system, right? It's not actually going to be affected by those contact forces, right? So our energy of our system is going to give us a way to ignore all of these nasty forces that are popping up between these connected bodies, okay? So we can ignore unnecessary or extra forces that aren't important to us. Okay, we could just take a look at the system as a whole, all at once, okay? So it's going to give us a really nice way of dealing with these super complicated problems. What it's going to produce at the end produces a set of differential equations identical to F equals ma, okay? So the result that it gives us will actually be exactly the same thing we would get from F equals ma, right? The actual physical laws still fundamentally the same. All that we're saying is this time we're going to ignore all this unnecessary stuff. We're going to try and take a look at it through this easier lens of energy for all these complicated systems. Okay. So before we actually get started and like do some math stuff related to Lagrange, do you guys have any questions about like the setup or the background for Lagrange's equations? Alrighty, cool. How about on the Zoom chat? How are you guys doing? Nice. Okay. So what we're going to do now is we're going to prove for a very simple case that Lagrange's equations and Newton's laws are actually the same thing, F equals ma. Okay. So let's prove that Lagrange and F equals ma are the same. Okay. So we're going to do this for a pretty simple case, just a particle moving in 3D space. All right. So let's say that we have a particle right over here. We have like a coordinate frame like that. That's our X, that's our Y, that's our Z. And we have gravity acting down, right? Gravity in the Z direction. Okay, so how can we get the differential equation that will help us solve for X of t, right? That's equal to our little x of t, little y of t, and our little z of t. Okay. So what we're trying to do is we're trying to solve a set of differential equations, or at least find a set of differential equations that will give us a path of this particle in time. All right. What I'm going to say, just to mix things up as well, is that we're going to have this force applied to our particle, F in R3. Okay. So this is a force vector with 3 different components, right? It's going to equal little Fx, Fy, Fz that are applied in each direction. Okay. All right. So our first thing that we want to do when we're setting up this Lagrange's equation problem is we want to pick something called a generalized coordinate. Okay. So our first thing that we're going to do is we're going to pick a generalized coordinate. Okay. So what is a generalized coordinate? Why do we want to deal with these things and what are they good for? Okay. So, normally when we're dealing with these Newton's laws, right, we take a look at them component by component. Right? Instead of just writing like an F equals like mx double dot, we'll write it out for each individual component. Right? We'll have like a force in the x direction is equal to mass times our x component double dot. Right? Force in our y direction, m times y double dot. Force in z equals m times z double dot. Okay. So instead of solving this thing all at once, we're breaking it up into these little pieces that we could deal with. Okay. So generalized coordinates are like the equivalent of splitting up our equations of motion for Lagrange, all right? So they help us split up our problem. Split up problem into fundamental directions. Mental directions. Okay, so we have to ask ourselves, what directions do we think our particle is capable of moving? Okay. And those directions are going to be the ones that we'll need to look at when we're doing our dynamics analysis, right? So here, if we look at this problem, our particle can move in X, Y, and Z directions, right? So because of that, right, it's able to freely move in all of these directions. Maybe we should be looking at X, Y, and Z as our generalized coordinates, okay? Because those are the only coordinates we're going to need to figure out where this particle is moving in space, okay? So they are the smallest set of coordinates. Sets of coordinates we need to completely describe our motion. Describe motion. Okay. So that's our general definition for what a generalized coordinate is going to be. Okay. So we picked out X, Y, and Z, because we know those are the only directions our particle can move in, right? Here it's just a simple particle. We're not going to have anything more complicated than that. Okay. So do we have any questions about like this generalized coordinate idea, what this is? Okay. So just remember, these are never going to be velocities, okay? These are just positions, just measures of some positions. Okay. All right, great. So our second step after this, right, is to apply Lagrange's equations. So No, it seems like we're really jumping the gun right there, right? We were just picking these directions of motion, then all of a sudden, boom, Lagrange's equations. Okay, so apply Lagrange. Okay. Yeah. Oh, R, sorry. Sure. Right. I'll give you guys a sec just to copy that down since some of you still writing a little bit. Yeah, so we're gonna show that they're the same for the case of the simple particle, and we're just gonna go through, calculate the equations of motion, and then see how F equals ma will pop out of that. Yeah, great question. All right. So, what are Lagrange's equations of motion? They're gonna look like this. Just gonna write them out here. Kind of look like a mess right now, but we'll break it down term by term. Okay. So we're taking the derivative with respect to time, the partial derivative, this thing called L that we haven't talked about yet, with respect to Q dot minus dL dQ. We're setting that equal to something called gamma. All right. There's a lot of weird stuff going on here. So these Q terms, these are any of our generalized coordinates. Okay. So any generalized coordinate. Right. So, all right. Now this gamma is going to be any external force. Force we apply in the direction of Q. Okay. So if we write like Q for, yeah.
Sorry, question. So what do you mean by general?
Yeah. So we call them generalized coordinates because it's just something that's trying to describe like a general motion in space. So normally when we define like a coordinate frame, right, we know that they're just going to be linear, components of motion, right? It's going to be like an X component, Y component, and a Z component. But we know that when we have physical motions, right, they're not always so easy or so natural to break up into these like X, Y, and Z's, right? It might be more natural to use a theta. So that's more of a general measure of position. So we call it a generalized coordinate. Great. All right. So we'll talk more about what we mean by like an external force right over here in just a moment, okay? But if you just want to have some idea of what this gamma is going into this problem, yeah, maybe just keep that, okay? So let's go through and let's take our first derivative, all right? And let's see if we can actually gain a physical intuition for what that derivative will be, okay? So let's take one derivative at a time of this mysterious quantity L, all right? So L is something that's called the Lagrangian for our system, okay? So L is called the Lagrangian. What it really is it's just a really nice way to deal with both kinetic and potential energy at once in our system, okay? So L is equal to T minus V, all right? So it's going to be the total kinetic energy of our system, so KE of system, minus our total potential energy of our system, potential energy of the system, all right? So we just subtract those two. And remember, since T and V were themselves both just scalar quantities, right? L will also be a scalar, okay? Scalar quantity. All right, so it's nice and easy for us to deal with here, okay? So let's calculate the Lagrangian for our simple system. And let's start taking a couple of partial derivatives. Let's see what goes on, okay? So just for the sake of looking at a couple of convenient terms in here, I'm going to take a look at the Z direction in this case. So let's try the Z direction for our derivatives. Right, the process is going to be the same and the meanings will be the same for the other terms. We're just going to talk about it here, okay? So first off, let's try and find our total kinetic energy for our system, okay? So T is equal to 1/2 our mass, velocity dotted with our velocity, okay? So remember we said that the total position of our system was just like an X, a Y, and a Z, right? And velocity, just going to be the time derivative of position. Oh yeah. Oh yeah. So maybe I'll just write that further down because at the moment I'm just trying to find kinetic energy. But what we're going to do is we're just going to solve this equation in here, hopefully to Z. Yeah. Right. So let's find our energies. Okay, so if our coordinate of our particle in R3 is x, y, z, right? Velocity is just going to be the time derivative. So like an x dot, a y dot, and a z dot, all right? So I'll just underline that so we don't mix it up with like our actual kinetic energy a little bit later, right? A little bit small, or excuse me, potential energy. Okay, so if we do this dotted with itself, right? What's that going to look like? 1/2 of m multiplied by our first component squared, right? X dot squared. Plus our second component, y dot squared, plus our third component, z dot squared. Okay, so that's our formula for kinetic energy in this case. Pretty easy. Okay. Now, what about our total potential energy, V? So once again, I'm just going to draw this as like a large V and have our velocity be like this little v over here. Okay. So our our potential energy for this case, remember, is just going to be our height in the direction of gravity. All right. So we need our height in the direction of gravity with respect to some sort of reference height. I'll just pick the origin right here to be my reference, so we get a 0. Okay. So V is equal to mgh, and gravity is going in our z direction over here. So I could just take that to be my z coordinate. Okay. mg times my height in the z direction. Remember, we're just saying that it's going to be relative to the origin of our system. We're just picking that reference point there, so it's nice and convenient for us when we write this out. Okay. Then our Lagrangian is going to be as simple as t minus v. Right? T minus v, 1/2 m x dot squared plus y dot squared plus z dot squared minus this term mgz. Okay. So that's a Lagrangian for our system. Now we're ready to start taking some derivatives. Okay. So do you guys have any questions about this process of finding Lagrangian right here? Or what do you think? Good. Yeah. Yeah. So yeah, it's a little bit of a can of worms to open, but it's essentially this idea that when you're looking at the changes of your Lagrangian and you write out this Euler-Lagrange equation right here, this is actually giving you the path of like least resistance or the path of least action in your system. So when you look at changes in the Lagrangian, you're essentially trying to minimize like your changes in kinetic energy. So you don't want to have like these crazy accelerations out of nowhere. That wouldn't happen in the real world. And you want to try and keep to a low potential energy, right? Because particles will naturally seek like a low height. Okay. So this equation right over here is actually something from calculus of variations. Okay. So if you tried the bonus problem on the homework, I think you would see this equation pop up in a more general form. But but that's okay. That's okay. Yeah. So all that this equation is saying is just that we're trying to find the smallest, amount of change in energy that's going to happen as we move our particle, right? Because particles are pretty lazy; they don't like to do a whole lot. Yeah. Sure. Yeah. 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 So we'll talk about that when we get to rigid body dynamics. Yeah. All right. Okay. So now let's try and take our first derivative. And interpret it. Okay, so when we look at this Lagrange's equation, right, we have a bunch of different derivatives to take care of here. I'm going to just start out with this term, this dl dq dot, and then we'll take its time derivative, then we'll do this other one. Okay, so let's start out by doing dl dq dot, and then we'll see what it means. Okay, so in this case, let's just do it in the z direction just to see what happens. So let's try in our z direction. Okay, so we're trying to take dl dz dot. All right, so when we take a partial derivative, remember, we just treat everything like it's going to be a constant except that thing z dot. Okay, so partial equals treat everything but z dot as constant. Okay, so we see that we have a z dot term coming up right there, right? This z dot. And everything else, right, just going to be a constant. So all those other terms are just going to drop out. All right. So what this is going to look like if I try and take the partial derivative of this whole thing with respect to z dot, is I'm just going to get an m times a z dot, right? So we're going to use power rule. We're going to say that the z dot squared will become a 2z dot when we take its partial derivative, right? That's going to get multiplied by the 1/2 m out here. So those twos are going to cancel. We're going to end up with an mz dot right there. Okay. So what does this first derivative that we've taken, the L dz dot, actually mean? Okay. So when we do the L dz dot, what is it? Okay. Remember earlier when we were talking about this idea of momentum, right? We saw that the momentum of a particle was equal to our mass times like our x dot, our y dot, and our z dot. Okay. And all that we have right here is we have an m times a z dot. Okay. So when we take dl dz dot, all that we're getting back is the momentum in the direction of our generalized coordinate. Okay. So dl dz dot is the momentum in the direction of our generalized coordinate. Okay. And this is something that will actually hold true for any single generalized coordinate out there that you pick, right? If we picked x and we took this partial derivative, we would get mx dot, which is going to be the component of our momentum in the x direction. If we took something with respect to theta dot, which we'll see later, we'll actually end up getting the angular momentum of our system in the direction of theta. And all of these great things, all these physical things, are actually going to pop out of our equation of motion. Okay. So when you see this dl dz dot or dl dq dot, yeah.
Sorry.
Yeah.
I guess I could got lost slightly. How did G relate to the other thing?
Oh, yeah. So G, which is our linear momentum, was equal to the mass times your velocity vector for your system, right? Your velocity vector is just x dot, y dot, and z dot in there, right? So if we multiply that out, right, that's like mx dot, my dot, mz dot. So if we look at the z component of our linear momentum, right, we see that it's just mz dot, which is the same thing that we got by doing this first partial derivative of this Lagrangian over here. So we found that when we took the partial derivative of our Lagrangian with respect to z dot, we actually somehow got our linear momentum in our z direction.
I guess one question are those for the trajectory now?
So I'm just starting out by taking it in z direction right over here, just because like a lot of nice things will come out for it, just to illustrate the purpose of a lot of these things. But we also have like our x and our y directions. Sure, yeah. Yeah, do you guys have any other questions? Yeah. Yeah, so we're going to see a z double dot when we take the time derivative of this thing later. But for now, we've just started out by doing plain old dl dz dot. So we've just taken the derivative of that. Yeah. Okay, yeah, great questions. Yeah, do you guys have any other questions about like this first derivative that we've done? Okay, so in summary, when we take that first one, when we do like dl dq dot, or q dot is like z dot, x dot, y dot, any of those, right? That gives us component of momentum along C. Okay. So whenever you're taking that, just remember that's actually related to a physical quantity. Okay. So now let's take its time derivative. Take d dt of dl dq dot. Okay. Well, let's try just doing that for that system that we were just looking at. Right. So now we're going to do d dt of dl dq dot, which was m times z dot. So now we're taking a time derivative, right? Z is a function of time. Mass is always constant. So that's going to give us an mz double dot. All right. So what does this represent? Well, now if we go ahead and we look at the acceleration for our system, right? That was an x double dot, y double dot, and a z double dot, right? All that this thing is right here, when we do ddt of dl dq dot, we just get our ma term of f equals ma in the z direction. Okay, so whenever we're actually taking this derivative over here, right, all that that's doing is giving us our ma in f equals ma. Okay, so even though it looks like this other crazy thing with partial derivatives, for every single system out there, every choice of generalized coordinate, this thing is just doing MA for us, okay? And by doing it, using this method of energy, we've avoided having to do any nasty stuff with vector calculus to actually figure out what that acceleration is. We just jump straight to our answer, okay? So just gives us MA. Gives us. All right. So do we have any questions about this ddt dLdq dot term? Okay. So overall, remember our Lagrangian equation was ddt dLdq dot minus dLdq equals this gamma over here. Okay. So far we've taken care of that. We saw that this was equal to MA. Okay. All right. Cool.
So we can just direction. Like you said that.
Oh yeah. So what I meant by that was that, like, if we're looking at a system like this, right, and we know that this is changing and this is changing, we're trying to find like the acceleration of your x double dot for that point. Instead of having to find all that stuff with vector calculus to get your mass times acceleration, you just use this Lagrangian equation, which just looks at the energy of your system to get that. Yeah. So instead of just doing like this awful vector calculus to get here, we're just saying, okay, we're just going to do this instead, and that's going to work out a lot nicer for us in a lot of cases.
Oh, okay. I see. I think vector calculus needing that station. Kind of like add the vector.
Yeah, or like taking like term by term derivatives of vectors and then their basis vectors.
Oh, I see. Would you still would that still be able to in what direction the object is moving?
Yeah, so we'll end up getting something that we interpret when we finish like filling out these terms over here. So it will tell us something.
This is what you mean is this ddt partial derivative dLdq dot is MA.
It's MA. Yeah,
Okay.
it's the MA part of F equals MA. All right. Yeah. How are you guys feeling about this? What do we think so far? Good. All right. Nice. All right. So now let's take the LDQ. Okay. So let me just copy my Lagrangian from earlier just so we can actually remember what it is. All the way up there. Copy this and paste. All right, nice. All right. So once again, I'm just going to do this in the z direction just because that's what we were doing before. Okay. So I'll do the z direction as an example. Okay. Just remember you would repeat this process for all of your generalized coordinates. Yeah.
Actually, yeah. The question is concerned that. So once we repeat that for every component of our generalized coordinate, do we stack them or just think about them as independent equations governing different different aspects of it?
Yeah, so you could stack them if you want, or you could keep them as different. It's just a matter of notation. Yeah, it's the same thing.
And it doesn't make sense to really take the partial derivative with respect to a vector, right?
So you can do that, but so if you take the partial derivative of a vector with respect to a vector, you end up getting a matrix. Yeah, yeah. So look out for that case. But if you do partial derivative of a scalar with respect to a vector, like if you have like I don't know, let me come up with this variable. I'll call it like I'm trying to think of things that we haven't used yet. We call it k, and I take like dk dq.
We do use
Q, or q is equal to like q1 q2. That's just going to equal like dk dq1 dk dq2. Yeah. But if k is a vector, I'm going to end up getting a 2x2 matrix out of this, which would be like dk1 dq1, and then like dk1 dq2, and then blah, blah, blah. Yeah.
Is that what a Jacobian does?
That's what a Jacobian is. Yeah.
Yeah.
I missed something very fundamental.
Oh, no,
The question was like,
yeah.
You can't take a.
So it's like, can you take a derivative of a quantity with respect to a vector?
You can, but it's all partial derivatives of each.
Yeah. So it's going to be like component by component. Yeah.
It's just like super interesting.
And that's what it would look like up there.
Yeah, so this is what it would look like if k was a scalar. You would take the derivative of k with respect to your first component and your second component. But otherwise, if it was a vector, you would actually end up getting a matrix where this would be k1, that would be k1. It's like dk2, dq2, q1, k2, dq2. Yeah. So we'd end up getting that.
That is what it is.
Yeah. Good. All right, great. Yeah, so let's try out the z direction right here. We're just doing scalars, okay? All right, so if I do dl dz, treating everything else as a constant, treating z is the only thing that's changing here, okay? So all of this stuff is going to knock right out, right? That doesn't have any z terms in it. The only thing we're going to end up getting is a minus mg, okay? So let's try and think about what a minus mg is actually representing, right? So if I have a particle, right, with mass m and gravity is pointing downwards, how do I express the force of gravity on that particle, right? This is going to be a minus mg going down, right? Okay, so that's what we have right here, right? So we had this idea that whenever we take dl dz, yeah. Oh yeah, so if you read an aerospace textbook, if you read the textbook, they'll take z 20 minutes. Yeah. It's covered. So I guess that's actually fun. So airline equals z bad. Otherwise equals z. Yeah. I guess it's just that whatever field you're in. Yeah. All right. So when we take this dl dz, what we're getting is we get the force associated with potential energy. Okay. So in this case, the only source of potential energy we have is a gravitational potential energy. Okay. So when we take this dl dz, what we get out is the force due to that gravity. But if in addition to this, right, let's imagine that I also had a spring that was on this, right? Like a plus 1/2, or excuse me, it would be a minus 1/2 kx squared, and, or let's say kz squared, just for the sake of this. And I take the partial derivative of that, right? I would end up with a minus kz on it, okay? So that would also be a force due to my spring, okay? So what we're getting when we do this dl dz is we get all of the forces that are associated with some source of energy in our system, okay? These are called energetic or conservative forces, okay? And we call them conservative because they actually only, yes, Mary.
Sorry.
Sure, yeah.
So is that really the idea of like energy is like a gradient of force?
So force is the gradient of
Okay.
an energy field. Yeah. Yeah. In general, if you define this, so we have like conservative forces. Conservative forces are gradient of a potential field, we call it. Oh, man, I guess I have nested quotes in here. But yeah, so in general, if you have some energy fields, let me just call it U here, right? You could find the force associated with it. Force due to U is going to be the gradient of U. Okay. And that's going to equal to like the sum of your vector directions, like du dxi multiplied by like your basis vector xi. Okay. Sure. So basis vec, and that's your the coordinate for one. Okay. Yeah, but yeah, don't worry about that here. So if you're dealing with any other forces or any other energy fields, like say you have like electric fields, you're actually working with orbital dynamics and you have gravitational fields, then this is something that you would end up using. But here we're just going to keep it nice and simple, so we won't have any of that stuff here. All right, awesome. Yeah, good question. Yeah. Yes. Yeah, so gravity would be a constant potential field. So gravity is like this thing like mgz, right? And if we take the gradient of, in this case, right, u equals, right, we don't have any x component, we don't have any y component, so this is just going to be a u dz in our z direction, and then we're going to end up with an mg z. So that's our force due to gravity right there. Yeah. So I think it's actually the negative gradient. Yeah.
Yeah.
Right. Sweet.
Physics 7B last semester, I should remember.
All right, great. Okay, so when we take this dl dz, we get back our energetic forces, right? Our forces due to these energy fields. When we take our dl dz dot, we get a component of our momentum. We take the time derivative of that, we get our mass times acceleration. Okay, so let's just fill in what we have so far in our Lagrange's equations. We have this ddt of dl dq dot minus a dl dq equals some gamma over here. Okay, so this is our mass times acceleration, right? This is our energetic force. And these are our external forces. Okay. Okay, so we're almost there. So for dl,
No, just at the bottom. Sorry.
yeah.
You.
Oh yeah, that's a minus right there. Yeah, because we're taking gravity to be pointing down. Yeah, not aerospace. What's up? You know, it's a kind of funny story. So I read this paper about a drone controller that was written by a guy in an aerospace department. And I was just trying to like implement it, and I was copying his code, or I was copying like the equation that they had written in there. And I was like, why isn't this working? Like it kept going down. And then like I asked this guy and he was like, oh yeah, that's an aerospace paper. They always take Z in the opposite direction. Yeah. But yeah, I guess that's just kind of funny. All right, cool. So from this, we can essentially tell that, you know, if this is our MA term, we know that this should be equal to our total forces F on our other side, okay? But at the moment, we have an MA minus an F conservative is equal to this gamma over here, all right? This is where we are in our position in Lagrange's equations, okay? So let me just bring over this thing to the side. So we have an F conservative plus this gamma, all right? And by F equals MA, right, this should equal our total force F, okay? So if this equals our total force F, what gamma is going to be, is it's going to be all of our non-conservative forces. Non-conservative forces in the Z direction, okay? So what it comes down to is saying, I'm actually like applying a force myself to this block, or maybe there's some sort of force that isn't due to the presence of some energetic field, right? Maybe there's like an air resistance or frictional force, right? Those are all going to show up in those gamma terms, because everything that's in gamma, that can't be something that's due to an energy field in there, right? That's got to show up in our conservative force, okay? So gamma equals all non-conservative forces. Non-conservative forces in the direction of our generalized coordinate. Okay, so for example, we can have like a friction force. The reason that that's not due to some sort of energy field, right? If I take my finger, I drag it across the table, and I move it back. I move it back to my original position. I'm not getting that energy back, right? I'm simply just burning up more energy when I move back. Same with air resistance, right? Move my hand over here, I lose some energy. I move it back, I don't gain that energy back by going to my original position. I work with gravity, right? If I move up there, down, back, all of a sudden I have the same gravitational energy. I've lost a bunch due to air resistance. Okay. So it's not due to one of those energy fields. So air resistance. So that would be one of these external forces or applied forces that will show up in our gamma term. Okay. So all up, what we sort of had in this case was we had an mz double dot, right? Plus an mg was equal to the component of that applied force in the z direction. Okay. So this gives us, a differential equation that we can solve for z of t. Okay. So if we solve that differential equation, we get an actual equation of motion where our particle is going in time. All right. So that's our overall process of representing and interpreting these Lagrangian equations for the simple case of a particle. All right. So how do you guys feel about that overall? Yay or nay? Okay. This is for number 2. Yeah. Sure. Yeah. Yep. Yeah. So when we look at a rotational term, it's not going to be a force, but it's just going to be a torque in that case. So gamma would be like a torque that we're applying to our first axis, or a torque that we're applying to our second axis in that pendulum problem.
Okay.
Yeah.
Like another sort of force that you have.
Yeah, like if we had like a bearing friction or something like that. Yeah. Yeah, sure. All right. So, okay, around 30 minutes left. Let's see what we want to talk about. Okay, why not? Okay, so do we have any questions before we do some rigid body dynamics? It's gonna get real. All right, sweet. So rigid body dynamics. Okay, so the stuff with the particle was great, right? But in the real world, things aren't particles, right? As much as we wish that they were, it's simply not realistic. Okay, so now our question is, how can we repeat this process for rigid bodies? So how to repeat for rigid bodies. Okay, so something that we can prove, we won't prove here, it's actually a really, really long derivation to go through this, but you can show that Lagrange's equations, once again, are equivalent to F equals ma for the case of a rigid body, all right? So Lagrange's equation still actually holds, miraculously. So Lagrange still holds, wow. Still holds for a rigid body. All right. So once again, all that we need to do is find that t and find that v, right? Then we can get our Lagrangian, start taking partial derivatives like there's no tomorrow, and then we're all good, right? So L equals t minus v. All right. So our main question now is, how do we find t for a rigid body? Find t for a rigid body. And how about v? All right. So before I draw a picture right here, I'll just mention something that Miriam told me the other day. So whenever I've been drawing a rigid body, she keeps thinking of a shawarma. It looks more on a rotation. Yeah. So I'll show you guys, because I haven't been able to stop thinking of that since you mentioned it. But yeah, I'll give you my best guess. All right. So we have our rigid body, and then an axis. But it's rotating around. And there you go. Which one?
Yeah.
So it's rotating around. It's the problem with having lost your dinner time. Yeah. Okay, cool. So let's talk about some problems that will arise in this case, right? What's gone wrong here? Why can't we simply just look at our formulas for kinetic energy for a single particle? Okay. So what's actually going on with this rigid body, right? Well, we know from earlier when we were talking about all these rigid body velocities, right? Let's say that our center can have some actual linear velocity in space, right? So it's like I'm taking my water bottle, moving it along like this, right? But it might not necessarily just have that, right? It might also be spinning about its axis as it goes along, okay? So now we have this translational motion, but we also have this spinning motion, okay? From earlier, what we know is that because we have this spinning motion, right, and because our rigid body velocity, or excuse me, because our rigid body has a shape to it, in general, every point on the rigid body has a different velocity. So when we go and we try to apply our familiar formula, right, t particle equals 1/2 m v dot up with v, what do, right? This v is going to be different for every single point on a rigid body. What v do we pick, right? How are we going to get around this sort of problem here? All right. So now we have this rotation and we have a translation. Okay. So I'm going to write something out. It's going to look a little bit messy at first, but we're going to break it down into a couple different parts and see where that stuff we've been using in homework comes from. Okay. All right. So first, I'm going to define the kinetic energy for a rigid body. All right. So definition: kinetic energy for a rigid body. Body is computed with the following integral. Ooh. So T is equal to 1/2 of the integral of rho v dot v dv. Okay. So this is actually a volume integral in 3D over the volume of my rigid body. Okay. So what this rho is in here is the density. Okay. V is the velocity of any point inside that volume. So velocity of any point in the volume in rigid body. And V is going to be like a volume or a differential element of volume is what we say. Okay, so now what we're doing is we're saying, all right, we know that if we take a density and we multiply it by a volume, what we're going to get is we get a mass back out, right? So looking at this formula, right, we have a rho times a dv times v dot v. So this is giving us a similar structure to 1/2 m v dot of its v, right? It looks pretty similar, right? We have this rho times this element of velocity. This time we're just going over our entire body because we have to account for all of these changing velocities on a rigid body. Okay. So do you guys have any just like conceptual questions about this integral here? How do you feel about this? So this is actually something that was just postulated, which just means that some guy just came up with it. And he was like, yeah, this looks about right. Granted, he was pretty spot on, pretty accurate, but yeah. Yeah, so when we perform this integral, we'll see we actually get a term that looks like that. But it's just like it was inspired by looking at that and saying that, okay, rho times the volume gives us a mass, right? We know we should have something that looks sort of like 1/2 mass times velocity squared. And we have rho times the volume, sort of like mass times velocity that we're integrating over this body. Yeah. Yeah. So you could think of this like one of these guys. So it's like a triple integral over our body that we're performing. Yeah.
Like in whatever three coordinates.
Yeah, exactly. Yeah. So I'm just going to denote that with that V down there. But it's like we're essentially blocking this up into little pieces. Okay. And then we're looking at it like 1 dV at a time. Yeah.
So the V on the outside.
Yeah, that's volume. Inside what's velocity. Yeah. Let me draw that a little bit smaller. V and V. Yeah. So sometimes you'll see like volume written with like a little cross underneath it. Yeah. I think that's what they do with thermal usually. But yeah. Okay. All right. So this integral, it sucks, right? We really don't want to deal with this if we can, right? So how do we avoid taking this integral? So how do we avoid taking this integral? Right? Surely there must be some sort of easier representation we could work out of this definition. Okay. So what's that going to look like? How are we going to get there? Okay. So one idea, right, is we could try and split it up into 2 parts. So split up into 2 parts. Okay. So we know that, right, when I was moving this water bottle around, it had some sort of translational component. It's also spinning about its axis, right? So maybe we could say we have these 2 components to our kinetic energy total, right? We could have a translational component, which I'll call like T underscore little t, okay, for translational. And yeah, like this little lowercase t over there. Yeah. And we could also have a rotational component, okay, T underscore R, all right? So this rotational component, if we want to get a physical interpretation for it, remember we had said earlier that when we just had this simple like kinetic energy for a particle, we said that was like how hard it was to stop it from moving. You can think of this rotational like how much energy is stored in the actual rotation, how hard it is. If this was spinning at a high velocity, something I just slam it to a stop. How hard would that be? That's sort of what our rotational kinetic energy is going to be. Okay. So we're going to find out what the formulas for these two things actually are by working a little bit with that integral. Okay. All right. So here's our main idea. We know that velocity is a vector, right? So velocity, just a vector. All right. So we know we can split up vectors into different parts, right? We can decompose them. So let's see if we can come up with any nice decomposition for our system. All right. What I'm going to do is I'm going to look at the velocity of the center of mass. Okay. So velocity of the center of mass, which we usually denote like with this little cross. It's like what they put on the crash test dummies. Like that.
Oh,
Yeah.
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 It's
Like a
mass, yeah.
Center mathematician.
Evans Hall. Yeah, so we put this little logo right on the center of mass, and we say, okay, I'm going to look just at the velocity of my center of mass, and I'm going to try and add on some component to that will represent the other velocities that are happening in my body. Okay, so we denote the center of mass with this little bar over it. So you actually find the center of mass by computing like the centroid of your body. So if you've done probability, you'll know that like taking the centroid of your distribution will give you the expected value, which is like the average, right? And to note the average, you usually put like this little bar over it like that. Okay. So I guess that's just kind of like a fun connection to that if you're into that sort of thing. But yeah, so we have this V of the center of mass, right? This V bar. So how can we use V bar to our advantage? How can we use V bar? Okay. So what we want to do is we know that in here, this is going to be a velocity for any point on our rigid body. Okay. So let's see if we can try and express the velocity of any point in our rigid body in terms of the velocity of the center of mass. Okay. So it turns out we can actually write it as the following. So velocity of any point is equal to the velocity of the center of mass plus your angular velocity vector cross product with this vector r. All right. So r is going to be the vector from your center of mass to that point in your rigid body. Okay, so we know that in the past we've always used this omega cross r to figure out some sort of rotational component of velocity. We're just doing that same thing over here. We're saying we can find the velocity of any point on our body by adding omega cross r to the velocity of our mass center. Okay, so it's just this term that will help us find out how quickly anything on our body is moving. All right, so let's try and plug this into the integral. Try and plug into the integral. Okay, so we know that t equals 1/2 integral over our volume of rho v dotted with v d volume. Okay, so plug in this new formula for v. So we have 1/2 integral v rho times now velocity bar plus omega cross r dotted with v bar plus omega cross r d volume. Okay.
Like that. You're the one we get a volume, right?
Yes. Yeah. Sorry. V. All right. So we're performing a volume integral, right? Volume integral over the body. Okay. So let's try and expand this dot product a little bit, and we'll collect it into two different terms. And integral over our volume here of, it's going to be, our first term will be rho v bar. Just going to distribute across like that. V bar dotted with v bar plus v bar dotted with omega cross r plus all these other things multiplied by each other. Okay, so I'm just going to pretend for now that you just collect all of that stuff in something called term 2. All right, we're not going to worry about it. So plus term 2, all multiplied by differential of volume. All right, now split this up into two integrals, right? One over volume, rho v bar dotted with v bar d volume plus 1/2 integral over our volume, rho times term 2 d volume. Okay. Now we're performing this integral right over here over our entire volume of our rigid body, right? It's moving around all over the place, collecting all these little different volume pieces. Okay. But this thing right over here, does our velocity of our center of mass depend on that? No, right? Velocity of our center of mass is just a constant, right? It's just a constant. Okay, so we can actually pull that out of the integral like we would with any other constant, right? So now this is equal to 1/2 v bar dotted with v bar multiplied by this entire integral, rho dv plus 1/2 v, rho times term 2 dv, okay? So what's the integral of density over a volume? Anyone know what that'll give us? Yeah.
Yeah, math.
Mass. This is mass. Okay. So this is 1/2 m velocity of the center of mass dotted with the velocity of the center of mass. Okay. And then we're adding on the second integral over here. Integral of rho term 2 dv. Okay. Remember, this is equal to our total kinetic energy of this rigid body. All right. So I'm going to write out just the next step in this process over here. It's going to look like a little bit of a jump. And oh yeah, okay. Let me know when. All right. And it's going to actually come from a lot of algebraic manipulation that I don't think is hugely illuminating. So we won't go through it here. Also, it's big pain. All right. So we can actually show that we can simplify this second integral over here. So we can get the following expression. V bar with V bar plus 1/2 of omega transpose, this thing called I center of mass times omega. All right. So this is going to give us our entire kinetic energy for our rigid body. Entire kinetic energy for a rigid body. All right. Now, this is an entirely closed form over here. All right. We don't have a single integral remaining. So this is a nice and easy expression for us to work with. It's going to be great for us as we go ahead in our dynamics problems. Okay. So this first term over here is 1/2 m v bar dot v bar, right? That's going to be our translational kinetic energy. Okay. So translational kinetic energy. And this term over here, omega transpose I center of mass omega, is equal to TR. All right. That's our rotational kinetic energy. All right. So for a rigid body, when we're trying to compute these energies, the center of mass is a really, really critical point for us. Okay. We try to compute the translational kinetic energy of that rigid body. It's going to come just from looking at the velocity of the center of mass. Now, if we try to do the rotational kinetic energy of that rigid body, it's going to depend on something called the inertia of the center of mass. Talk about it in just a sec. Okay. All right. So do you guys have any questions about how we got to this stage right over here? Yeah. Yeah, so this term over here will have like your omega cross r's, but dotted with omega cross r, and it's going to have like plus 2 times like v bar dotted with omega cross r. And this whole thing is going to be like integrated over your volume. And you could show via a lot of simplification on that side that you can essentially pull out this constant matrix called like I over here and have it so that it'll just like factor into this really nice form like over here. So yeah, it's essentially just going to come like out of this thing. So it's called like a quadratic form. And essentially what it means is that this is a form such that you could factor out a factor on one side, factor out a factor on another side, and have a matrix in the middle that is performing this entire like dot product operation for us. And it's really just you're hard calculating things, and you're able to simplify it into this nice book. Yeah. Yes. Oh, yeah, right. These are all just integrals over the volume right on there. Yeah. Yeah, all the same. Yeah, thanks. Oh yeah, same integral. Yeah, sure. Yeah. Oh, okay, cool. Yeah, sorry about that. All right. So what is this I center of mass? All right. So let's try and take a look at what the shape of it should be. Okay. So the shape. Well, we want to multiply it by this omega vector. So we want to multiply by omega element R3 on one side. Okay. And we want to multiply by an omega transpose on the other side. Okay, so what we want is we want this matrix. It's going to look like the following, all right? Okay, so we're going to have one term here, one term there, one term there, one there, one there, one there. Okay, and what this tells us, just from the shapes of matrix multiplication, is that this thing in here, I center of mass, must be a 3 by 3 matrix. 3 by 3 matrix. Okay. So it's something called the inertia tensor for your system. Inertia tensor.
What is this?
Yeah. So tensor, it's like a somewhat generalized version of what a matrix is. So it's something that describes a transformation that isn't attached to any coordinate system in particular. So in this case, this inertia is a physical property of your mass. So like no matter what coordinate system you're looking at, it's still referring to that same physical property in there. Now, when we write it as a matrix in matrix form, it's actually going to look like, yeah, in that case, it's actually going to look like some sort of matrix with respect to a vector system. But there's this general, like, I don't know, like idea that that matrix is pointing to. So you can actually rewrite the inertia tensor in terms of like the Kronecker product. So can rewrite in terms of your Kronecker product.
Kronecker?
Yeah, so that's like the thing that looks like that. so it's this special thing that looks like same guy, yeah. So it looks like one of these, and it helps you write it out in the general form that will actually apply to any vector out there, no matter what basis that vector is in. So we're not going to talk about this stuff at all in here, but yeah, I mean, it would sort of look like, I don't know, like I is x, like x part of x plus like I, y from y plus some other stuff. Okay, so don't worry about this stuff for now. But yeah, if you're interested in what a tensor is, yeah, it's just this thing that you're able to apply to like any vector out there. In our case, we're just representing it as a matrix, just because that's nice and easy. We all know how to do matrix multiplication. Yeah. Yes. So they can have lots of different dimensions. So if you have like a first order tensor is like a 3 by 1 vector. Second order looks like a 3 by 3 matrix. So the inertia tensor is like a second order tensor. So there's lots of different ones that show up. Yeah. 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 So yeah, so I mean, yeah, we just talked about it super quick. So, like, if you're looking at the stress on the surface, you're gonna have like these shear forces, and then like your normal forces. So this isn't on the class, by the way. This is totally off topic. So we're gonna have all these different forces over here. Yeah, and I think that the stress tensor is a transformation from like shear like into like is it like shear into force or something? Do you remember? I know too. Yeah, so it's like shear into either like a force, or sorry, it's from your strain, which is like how far you're pulling the surface on your little cube, into I think your stress force. Okay, so the reason that it's not a force is that your stress tensor is actually a transformation that's happening at each point on your body. Like if I pull this, if I take this and I bend it right over here, this point will have a different amount of deflection due to that bending than this point over here, right? So we actually need a transformation to represent the stress that we're going to get in the paper back out. So I think so. Maybe check that out. But yeah. Okay, cool. Yeah, don't worry about this stuff. So if you're interested in this stuff, you could take ME C85, ME108 or ME185. Okay. So you'll see a lot of it in this class. I haven't taken it, but I've heard good things. So, all right, very cool. What are we talking about again? Yeah, sure. Okay. Okay, cool. Oh, inertia matrix. Thank you. Okay. So what is the inertia matrix? Okay. So when we write it out in forms, remember we had found out that it looked like this 3x3 matrix, right? So we have this I center of mass is equal to IXX, IYY, IZZ, IXY, IXY, IXZ, IZ, IYZ, IYZ. Okay, so it's going to look like this following thing, right? What each of these terms in here is telling us is how hard it is to rotate a rigid body. Rotate a rigid body about each axis. Okay, so let's say that my z-axis is pointing upwards, right? If I want to figure out how hard it is to rotate it about that z-axis, what I'm going to look at is this term right over here, IZZ. Okay, so IZZ is what's referring to a pure rotation about our z-axis. Okay, so rotation about z. Now our IYY, similarly, if I were to rotate it about my y-axis. Okay, so that's your rotation about y. Rotation about y, and then IXX, as I'm sure you can guess, is rotation about x. Rotation about x. All right. So what all of these off diagonal terms are, right? The ones that have yz, xz, all these things are, okay, is that our rigid bodies are not perfectly balanced about these axes of rotation, right? Like say, just for example, like I have this thing over here, but I'm trying to rotate it about the z-axis, right? Z-axis is not going symmetrically through this thing, right? It's now at an angle. So if I try to rotate it about the z-axis, what I'm going to end up with these little wobbles that are happening around my other axis as well. Okay. So what these other terms are telling us are essentially how balanced our object is going to be about these particular axes. Okay. So XYZ, right? Like how balanced our object is with respect to the axes. Okay. And if I do a pure rotation about the z, am I going to start ending up with some wobble about the y-axis as well? If I will, then my IYZ term is going to be non-zero. If I rotate it about the z and my IXZ term is going to be non-zero, I end up with some wobbling happening about my x-axis as well, even though I was just trying to rotate about z. Okay. So this term is essentially, or this matrix is just telling us everything about how our object is going to spin, right? So it's like how hard it is to spin it, and whether these little wobbles, these little vibrations are going to happen, accidentally. We're trying to rotate purely about one axis. Okay. Yeah. Okay. Yeah. So that won't be your center of mass matrix in this case. So what you're going to do in control is if you have like a system like a mass on in like a damper, right? You can actually rewrite this as a set of linear differential equations, like in the form x dot equals ax. And then if you find the eigenvalues of this matrix, that'll tell you your resonant frequency in that case. So the complex part of your eigenvalues, the vowels of A are your resonant frequencies. Yeah. I don't think you guys talk about it. Yeah. So yeah, so this thing is actually just symmetric about so it's going to be a symmetric matrix, and the reason for that is you could think like, okay, rotating about xy is going to have the same effect as rotating about yx, right?
So if I feel like a put these here,
yep. Yeah. Oh, IXY. So IXY and IYX are going to be the same thing. So it's a symmetric tensor. Yeah. Yeah. Okay, great. Do you guys have any other questions about this inertia term? Yeah. Oh, like a diagonal matrix,
I
or
don't know, like, I guess.
Oh. Yeah.
I don't know.
Oh no, so that's never going to happen. It's always going to be symmetric, and it's going to be positive definite as well, which means all eigenvalues are going to be greater than or equal to 0, or just greater than 0 actually. So if you diagonalize this matrix, what that's going to do is actually, like, those eigenvectors, when you diagonalize it, are going to give you the axes of perfect rotation about your matrix. Okay, because when we just have a diagonal matrix, we know when we rotate about one of those axes, we're not going to get any wobbles, right? So if we find, say, the inertia tensor for my water bottle, right, and then we diagonalize it and we get some new directions, it turns out that those are the directions my water bottle can rotate perfectly about with perfectly smooth rotation.
What is it?
Oh, resonant frequency. Res. Yeah.
Resonant frequency.
FREQ. Okay. All right. Cool. So yeah, so if we go back to our form from earlier, 1/2 m v bar dotted with v bar plus 1/2 omega transpose I omega, right? And we think back to our interpretation of what a kinetic energy is, right? Is how hard it is to, like, slow down an object as it's spinning or as it's translating. The reason for this I matrix in here might become clear, right? Because the terms of I equals, like, how hard it is to rotate about an axis, right? So how hard it is to rotate about an axis. Okay, so what we're doing is we're combining that difficulty of rotating about one of these axes, we're combining that with the rate at which this thing is spinning. Okay, so if it's spinning super fast and we have these really high terms in our inertia matrix, right, that's going to tell us it's going to be super hard to slow that thing down. So it's got a lot of rotational kinetic energy. Okay, and then our kinetic energy, or translational kinetic energy, we could just interpret in the same way as before, right? Now, all that we're interested in is just the center of mass. Okay. All right. So do we have any questions about the potential, or excuse me, the kinetic energy for a rigid body? I know we took a couple of tangents in the middle, but yeah. Yeah, so that ends up, like, the reason we could pull it apart just comes from, like, an integral being linear in two different terms. And then there's a couple of vector identities that you could end up using to, like, simplify it out kind of nicely. Yeah. Yeah.
I'm gonna withdraw my question.
Oh, okay. We only have a couple of minutes left, actually. So if you want to ask it, then yeah, go for it.
Okay. Oh, so I was like the inertia matrix, like.
Oh, so your M matrix is something that's slightly different. That's actually a great point. I could talk about that instead of doing practice problems, because I don't think we'll have time for that. So yeah, so there's two different. I don't know. They name a lot of things kind of similarly in this class, which is kind of unfortunate. So if you ask you for inertia matrix in context of energy, so energy, then it's going to be this one I, okay, that we were talking about up here, I about your center of mass. But if they ask like in terms of equations of motion, it's going to be this capital M. It's going to get, like, multiplied by this Q double dot over there. Okay, so in your homework we were asking for this one over here. All right, so if you're ever wondering, just ask us and then we'll clarify. Yeah, sure. All right, cool. So let's just talk about our potential energy real quick, and we'll talk about a general way to organize these problems where this big M matrix comes up. And yeah, I think we'll leave it there. All right, so potential energy. We're essentially just asking ourselves, imagine that all of our mass was, like, concentrated at one point, okay? So if we have, like, some rigid body like this, right? Let's just concentrate all of our mass at one point. And then let's just focus on the height of that point, okay? We'll just use the height of that point to figure out what our potential energy is, right? So normally we had said that V was equal to mgh, okay? Now, if this is like the Z height, and we have, like, gravity pointing downwards, right? And our gravitational potential energy for a rigid body is just going to be mg times the z coordinate of the center of mass, all right? So we just look at center of mass, look at center of mass, because that's where it looks like all of our mass is collected, okay? So all mass is centered or collected there, okay? And if you want to reason about this sort of intuitively, right? It's like if we take a point up here, that's going to have slightly higher potential energy, right? But then if we take some point down here, that's going to have slightly lower potential energy. So if we want to find one point that will encompass the potential energy of this entire system, we just pick the center of mass because that's where everything is going to balance out. Okay. All right. So here, energy balances around center of mass. All right, great. Okay, so super quick, we could talk about like this general like mq double dot plus cq plus n equals gamma formula that we asked you for on the homework. And yeah, after that, I can stick around for questions if you guys have any. Okay, so our main question here is, right, we might have found our differential equations from Lagrange now. Now we might want to organize them in some way, okay? So how can we organize? We organize our equations of motion. Right? Whenever we solve one of these problems, we're going to end up with these crazy equations of motion, but are there any sort of recurring patterns that are going to appear in any of those? If so, what are they? So it turns out that for every system that we can apply Lagrange's equations to, we can actually factor it out into something that looks like the following. mq double dot plus cq dot plus n. What's this gamma over here? Yeah. All right, so these things are actually functions. So they're matrices that depend on our generalized coordinates. Okay. And Q in this case is a vector of all of our generalized coordinates. Okay. So Q is a vector of our generalized coordinates. Okay. So it could be like an x, a y, and maybe like a theta if we have some sort of rotation going on in our system. Okay. All right. So I'm just going to go ahead and talk about what each of these matrices represents here. So like mq double dots, let me just rewrite that real quick. cq dot plus n equals gamma. All right. Okay, so this one is what's often called our inertia or mass matrix. Okay, so if we look at mq double dot, right, what does that look like? Well, that looks like our ma term in our equations of motion, like mass times acceleration, right? And that's really what is represented. We know that in every system, we're sort of going to end up with one of those mass times acceleration terms, right? It's going to look slightly different for the rotational case. It's going to be an inertia times the angular acceleration in that case. So looks like an inertia times like your theta double dot for rotation, for translation. Okay. And it's going to have all of those F equals ma looking terms, right? So if you ever want to identify where that ma is popping up, then we just put that into our mass term, all right? So what this mass matrix is telling us is gives info about m, and it gives info about the components of our inertia tensor, okay? So m is essentially telling us everything about how hard it is to move our body, right? If I have something with super high mass, I need to put in a really, really high force to move, right? I'm going to learn that from my m matrix. The entries are super large, okay? Now, similarly, for a rotational term, if I go ahead and I look at my theta component, right? Third row of my mass matrix, right? If those terms are super high, it's going to be pretty hard to rotate my rigid body as well, right? High rotational motion. All right. So it tells us everything about how hard it is to move our system, right? Now, Coriolis, I'm going to skip just for a second, and then we'll come back to that. So n will be a vector of all our conservative forces. Conservative forces, okay? So we saw that when we did Lagrange's equations, right, a while ago, we found that when we did those, dl dq terms, we ended up getting our conservative forces coming back out. Now, all that we're saying is that our n is going to be like our first term, like dl dx, dl, dy, so on and so forth. Okay, so this is sometimes called the gravity vector. So gravity vector, because gravity is like the classic example of a conservative energy-based force, right? And that's why we give it that name. All right. But yeah, just remember, it's not only going to be gravity in there. If we have something like a spring force or anything else that's coming from a source of energy, that's also going to be showing up in our end term, right? So gamma is going to be our external or applied forces. Okay, so just remember these were all of those forces that weren't depending on some energy field being there in space. Okay, so don't depend on an energy field. All right. So something that's important to note is that gamma is called like a generalized force vector. All right. And the reason that we say generalized is that because when we're looking at like these equations, right? Oftentimes we have both a translation and a rotation going on, right? So when we try to generalize the idea of a force, we're looking not only at the linear case where we're just moving around, but we're also looking at the angular case, right? So for an angular case, like angular equivalent of force is torque, right? So this vector gamma over here, since it's one of these generalized vectors, it's not just going to have forces in it, but it could have torques as well if we're going to be having some sort of rotation happening in our system, okay? So gamma could have forces and torques, all right? And whether it will have a force or a torque in a particular entry will just depend on whether that entry will correspond to an angular generalized coordinate, if we had a theta in that particular row, or if we had like an x or a y in that particular row, right? An x and y will give us a linear force because that's what they need. And one of those theta entries will have a torque, right? Because it needs a torque for rotation, all right? Okay, so do you guys have any questions about those three before we talk about Coriolis? How do we feel about these? Good. Coriolis. So what is the Coriolis? All right, so where does this Coriolis term come from? What does it represent? All right. So if we take a look at our system up there, right, where we have this mq double dot plus cq dot plus n equals gamma, right? And let's say we bring our n like over to this side, right? We're going to end up with something that looks like mq double dot equals some set of forces, right? And this looks like we should be done right here, right? This looks like it's F equals ma, right? So it looks like F equals ma. Why do we need? We need a CQ dot, all right? So here's one problem that's going to come up, all right? When we try and look at, coordinate systems that are really convenient for our natural motion, right? They're not often going to end up playing nice with these ideas of derivatives and, taking derivatives with respect to vectors and all this stuff, okay? So let me just show you guys what I mean by that. So if we take like a particle system, it's just like that, right? Just moving around x, y, and z. We take like x, y, z generalized coordinates, right? The position of that particle is just going to be like x along our x hat direction, plus y along our y hat direction, plus z along our z hat direction, okay? So this is just like a unit vector in x direction, all right? And I go ahead and I take its derivative, again, and I get its acceleration, p double dot, x double dot, x hat direction, plus y double dot, y hat direction, plus z double dot, and the z hat direction, okay? Now I was able to do this and keep it in this really nice and simple form because these basis vectors are constant, all right? So basis vectors are constant, all right? So if these were actually our only three generalized coordinates, right, this would be enough to cover our entire thing, right? We would actually have zero Coriolis term. All our basis vectors, they're always pointing in the same direction. So when we try and figure out our acceleration, right, just going to depend on our double dots, okay? So acceleration for F equals MA just depends on like our Q double dot terms. Oh, yeah, sorry, something. Oh, yeah, constant. Sure. All right, but what about if we look at another sort of system, right? Now, let's say that we're looking at a system that looks like this, right? So say we have one axis that's pointing over there, one axis that's pointing over there. Now we have, or yeah, let me make it a rigid pendulum that's swinging around, okay? So we might want to figure out, like, all right, a generalized coordinate is going to be real nice for us. In this case, is just going to be this angle theta, okay? So when we take this angle theta, how do we express acceleration in terms of theta, right? Because we still need an xy acceleration to figure out what's going on here, right? Still need an x double dot for this case. So when we actually compute this, right, it's almost as if we have like a basis over here that's moving around with our system, all right? So we have like a moving basis, okay? So it's like we're representing our entire system in polar coordinates whenever we're using one of these angles here, okay? Like polar coordinates, okay? And the problem is that when we represent our position, right? Let me call this like ER, okay? That's going to be that vector that's pointing out like radially in polar coordinates. Let's say that the length of our arm is n. If I represent the position of my particle, right? Say I'm trying to figure out that position right over there. It's going to be our length L multiplied by our basis vector ER. When I go to take its first derivative, right? D dot, it's length of the bar changing, time derivative multiplied by ER. But now my ER is actually changing with respect to time, right? If my pendulum ends up swinging over here, my basis vectors are now going to be pointing in that direction over there, all right? So our basis vectors themselves are actually shifting with time when we take one of these rotational coordinates, right? So the time derivative of this ER is actually going to be non-zero. We have to account for that, okay? Same thing happens when I take the second derivative again, okay? So it could be constant. I'm just taking it as like changing in time, just to, I don't know, generalize here, but yeah. So in this case, just going to be a bunch of product rules. L double dot ER plus L times ER dot plus L dot ER dot plus L ER double dot, okay? Now, these ER dots, ER double dots, they depend on theta and our theta dot, okay? So even though we're just trying to represent our acceleration here in terms of, you know, this simple like theta double dot, a simple angle that's changing, we end up with all of these other terms that are popping up, these thetas, these theta dots, because we chose this rotating coordinate system to make our dynamics equations really nice, okay? So because of this changing coordinate system, our acceleration in F equals ma becomes messy and doesn't just depend on our theta double dot, okay? It also depends on theta and theta dot, okay? So what our Coriolis matrix is doing is it's collecting all of those theta dot terms that go into our acceleration, all right? So when we do C times Q dot, right, it essentially collects all of our theta and theta dot terms that contribute to acceleration, all right? So this Coriolis appearing is just a byproduct of having this rotational coordinate system where suddenly our theta double dot isn't enough to cover our entire acceleration term, all right? Okay, so how do you guys feel about Coriolis? What do you think? Does that make sense? Like why we end up having the need for that extra term in there? Okay. So just remember it can be zero, and it will be zero when you just have like a constant linear set of basis vectors like x, y, z, nothing else. So you guys probably would have seen in the first problem on the homework, you ended up with a c equals 0 in that case. That's just because we were taking a single a, or excuse me, a single x pointing in a single direction, right? Never changed. Oh yeah. What's that? Oh, so not quite. So when we do this m times the q double dot plus c times q dot, and say like we have a theta term in there, if we just do like our mass matrix term times our theta double dot, that's actually not going to cover everything we need to figure out like our acceleration, right? Because this thing, it has all these terms like an ER dot, an ER double dot that we need to figure out the acceleration. Oh, are we guys? I think there's some people out there. Yeah, sure. Yeah, so we have like all of these terms over here that we need to compute like our acceleration, right? So just multiplying our mass matrix by this theta double dot won't be enough to give us our entire acceleration term. We know we also have all these other terms that depend on theta dot and theta itself. So that's what our Cartell's term does. Yeah. So not enough. Cool. Alrighty. Yeah, let me stop the recording here.